In this video, let us look at what idempotent matrices are. A matrix A is called an idempotent matrix. Idempotent matrix if A square is again equal to A. So if you have a matrix A, square it. If you get the same matrix again, we call it an idempotent matrix. For example, if you have a matrix A as 2, 2, minus 1, minus 1. You have this matrix. So let us try to calculate A square. A square is equal to 2, 2, minus 1, minus 1 times 2, 2, minus 1, minus 1. That is equal to, so first row into first column. 4 minus 2 is 2. First row into second column. Again 4 minus 2 is 2. Second row times first column. Minus 2 plus 1 is minus 1. Minus 2 plus 1 is again equal to minus 1. So as you can see, you got the same matrix A. Hence, this matrix is called an idempotent matrix. So if A is an idempotent matrix, A square is equal to A. As a corollary, you can say that A to the power any number is equal to A. Because, for example, if A is an idempotent matrix, I can also say that A cube is equal to A. Because A cube is nothing but A square times A. A square is equal to A. So this is A times A is equal to A square is again equal to A. So if a matrix A is idempotent, by definition A square is equal to A. By corollary, by simple extension, A power any number, any natural number is always equal to A. So this is a basic definition of an idempotent matrix. So let us see some very special properties with respect to idempotent matrices. So let us look at the first property of idempotent matrices. So if A and B are idempotent matrices, then AB is idempotent if AB is equal to BA. A plus B is idempotent if AB is equal to BA is equal to 0. For example, by this property, if A and B are idempotent, that is A square is equal to A and B square is equal to B. So what this property says is AB will also be idempotent if this happens. So let us see whether this works or not. So AB whole square is equal to AB times AB. So as long as you don't change the order of the matrices, the brackets can be placed as you like. That is equal to A times BA times B. And if AB is equal to BA, by chance if AB is equal to BA, BA can be written as AB. Now I'll change the brackets like this. So as long as I don't change the order, I can place brackets as alike. That is equal to A square, B square. And A square is equal to A and B square is equal to B. So you get AB. So AB whole square is equal to AB if AB is equal to BA. So if AB is equal to BA, you can see that AB whole square will be equal to AB. Hence AB is an idempotent matrix. So the same thing can be thought of for A plus B. So A plus B whole square is equal to A square plus AB plus BA plus B square. So A and B are given as idempotent matrices. So A square is equal to A and B square is equal to B. And if AB and BA are both 0 matrices, then A plus B whole square is equal to A plus B, hence A plus B is also an idempotent matrix. So the next two properties are, if A is an idempotent matrix and A plus B is equal to I. So if A is an idempotent matrix and A plus B is equal to I, then B will also be an idempotent matrix and AB is equal to BA is equal to 0. That is, if you have A as an idempotent matrix, a matrix B which is I minus A is also an idempotent matrix. So if A is an idempotent matrix, I minus A will also be an idempotent matrix and AB is equal to BA is equal to 0. And the next property is, if AB is equal to A and BA is equal to B, then A and B are idempotent matrices. Let us look at these properties. So A is idempotent, that is A square is equal to A. Then A plus B is equal to I. If this also is valid, then B is idempotent. That means you need to prove that the matrix B, which is equal to I minus A, is also idempotent. So if A is idempotent, I minus A is also idempotent. I think this is very easy to prove. So you just need to prove that I minus A whole square is equal to I minus A. So can you prove this? Yes. So I minus A whole square, I and A are commutative. So I can directly expand it using the binomial expansion. I square minus 2AI plus A square. So I square is I minus 2A plus A square is same as A, because A is assumed as idempotent matrix, that is equal to I minus A. So I minus A whole square turned out to be I minus A, and B, which is equal to I minus A, is also idempotent. And AB will be equal to BA is equal to 0. So what is A times B? B is nothing but I minus A minus A square, which is A minus A, will be equal to 0. And the reverse, I minus A times A will also be equal to 0. So this is the second property. And the third property is, if AB is equal to A and BA is equal to B, then A and B are idempotent. So as you can see, so AB is equal to A and BA is equal to B. So A square is equal to, so A is AB, so A square is AB times AB, that is equal to A BAB, and BA is equal to B, so this can be written as ABB. So if I place bracket here, so AB is equal to A, this is equal to AB, and AB is finally equal to A. So AB is equal to A and B square is equal to B implies A square is equal to A. That means A is a idempotent matrix. So similar derivation can be done with respect to B also. So if AB is equal to A and BA is equal to B, then A and B are idempotent matrices.